Well, hello, and welcome to the latest in our series of live Mighty Low Carbon Energy Center webinars, coming to you from sweltering virtual MIT scattered across Massachusetts. Today's webinar, based on cutting-edge modeling work, examines the role of hydrogen in the low-carbon energy systems of the future. I'm Robert Stoner, the Deputy Director of Mighty for Science and Technology, and I'll be your moderator today. Our intention in presenting these webinars is to cover a range of topics drawn from ongoing work in all of Mighty's low-carbon energy centers, and a few drawn intentionally from outside them. We want you to know what we're up to at MIT, and what we think is especially interesting and important as we work toward a globally decarbonized energy system. And because we want to engage and hear from you, we've reserved time at the end of the session to answer your questions, and you can pose them at any time on the Zoom Q&A feature. We understand that not everyone will be able to view us live, and so as usual, we'll be recording the seminar so that it can be viewed offline later and shared with your colleagues. And please do share it. So what about hydrogen? Hydrogen is a rare potential clean energy panacea, an answer to many, if not all, of our clean energy concerns, with the potential to enable the decarbonization of many parts of the global economy. It can be used to store electrical energy on the grid for long periods, to power vehicles ranging from automobiles to ocean liners and airplanes, and to provide process heat for a wide range of industrial processes. Hydrogen is also used widely as an input to industrial processes, including oil refining, and chemical manufacturing. And it can be mixed with natural gas, distributed through existing gas pipelines, and consumed by existing and modified gas turbines to produce electricity and heat. In other words, hydrogen already has sizable markets, and because it is compatible with existing infrastructure, its pathway to deployment at significant scale appears to be relatively facile and therefore feasible in the near term. To be sure, we face many challenges in bringing hydrogen to the necessary gigantic scale of tens of gigatons per year of avoided carbon emissions, but the opportunity to do that has attracted the serious interest and investment of many large and varied firms. Our speaker today is Dr. Derek Malapragada, an MIT research scientist and one of the leaders of the Mighty Energy Systems Modeling and Markets Group. His current research interests focus on advancing energy system modeling tools to study the implications of renewable integration on the power sector, economy-wide electrification, and the assessment of emerging energy technologies. Derek, thanks for joining us today. Take it away.
Great. Thank you so much for the introduction, Rob. Hello, everybody. I'm just going to get the mechanics of this system up and running. Great. So I'm hoping everybody can see my screen. Good morning, everyone. It's a pleasure to be here and share some of our research work ongoing at Mighty in the topic of hydrogen, particularly focused on trying to understand what potential pathways based on hydrogen could impact a future low carbon energy system. So the work I'll be presenting to you is a collection of research that is done by a group of us at Mighty, and I'll highlight some of their names as I go along. So I'd like to start with just some context of where hydrogen might fit into the global energy picture. And so to understand that context, it's worth looking a little back and understanding where we are, the trajectory we have been taking with respect to emissions reduction in the energy system globally, but also more pertinently in the US where we are resided. So if you look at the last 10 years, we have seen sort of both in the US and globally, significant reductions in emissions from the electricity sector, largely driven by the adoption of wind, solar resources and their continued scale up. But also—
I point out that you haven't yet shared your screen.
Oh, okay. Sorry about that. Yeah. Let me try to fix that. Can you see my screen now?
Got it.
All right, my apologies for that. So as I was mentioning, the emissions trajectory across the various end-use energy sectors has largely been a story about emissions reduction in the electricity sector and relatively little progress of emissions reduction in the other sectors. And the story of emissions reduction in the electricity sector is likely to continue as we see projections from various groups such as the International Energy Agency suggesting that we will see continued adoption of low carbon electricity supply sources in the electricity sector. So this has obviously raised a lot of interest in exploring electrification as a proxy for decarbonization of other end-use sectors. So if you think about where electricity is used in final energy across the various end-use sectors, we see that it's predominantly present in residential and commercial applications and also in some industrial applications. But if you aggregate all of the electricity use as a contribution to final energy, it stands at about a fifth of total final energy use today. And if you look ahead, based on the same projections that I had mentioned in the previous slide, even under sustainable development scenarios, the contribution of electricity in final energy is expected to go up from about 20% today to about 30%, particularly with expansion of electrification of the transportation sector via adoption of electric vehicles. So this suggests that, based on the known technologies that we have today, there may be some limits of practically electrifying end uses, particularly in sectors like industrial applications and in heavy duty transport. So within this context is where hydrogen fits into the picture of larger decarbonization of the energy system. So there's been a lot of interest in exploring how hydrogen and hydrogen-derived energy carriers could enable decarbonization of various applications in transportation, industrial, residential, and commercial sectors. Now, these sectors are very varied in their end-use applications, notably that many of these applications, such as in transportation, are highly distributed in nature, while in the industrial sectors, many of these applications will be centralized applications. So some examples I've highlighted here include, long-haul transport for freight or passengers, which would be a distributed application. Residential space heating could be another distributed application, while in the industrial sector, providing both feedstocks, but also heat for various processes such as steel, as well as chemical manufacturing could represent large-scale centralized applications. So this is the story for hydrogen in and the potential uses in all the other sectors outside power. But it's also important to highlight that hydrogen could also play a significant role in the deep decarbonization of the power sector itself, particularly because of its ability to provide relatively cheap energy storage at relatively lower capital costs compared to known electrochemical technologies. So one configuration where hydrogen could interact with the electricity sector involves a system as shown here, where basically we have electrolyzers sourcing electricity from the grid to produce hydrogen that is compressed and then stored in either pressure vessels or in geological storage sites, which is already practiced today commercially. And subsequently, when during times of high electricity prices or relatively low wind or solar supply, the hydrogen could essentially be burnt in retrofitted combined cycle or open cycle power plants or fuel cell systems. This is a configuration that is being actively explored in many different jurisdictions. One other sort of point to note here is that hydrogen, because of its versatility of use in many end-use sectors, the same infrastructure could also be linked up with other end users of hydrogen. And some of the examples I'll talk about in our own analysis highlights that there is significant value to thinking of this sector coupling. So if we sort of take this vision for where hydrogen could play a role in the future energy system and compare that against where we are today with respect to a hydrogen focused economy, today hydrogen is a relatively niche contributor, both in terms of scale and in scope in the current energy system. So hydrogen supply globally is around amounts to 8 exajoules, which is relatively insignificant even if we compare that against US primary energy consumption alone. Most of that hydrogen tends to be used for refining of petroleum, other small amount in other industry, and to produce bulk commodity chemicals like ammonia and methanol. And more importantly, nearly all of that hydrogen comes from conversion of fossil fuels, with natural gas-based reforming being the dominant technology, both globally, but also primarily in the US. So this is the supply demand picture. Another challenge with hydrogen, especially if you think about distributed end users with respect to where we are today, is that there's relatively little infrastructure for its storage and transport, especially when you think about the scale of the energy system and the other energy infrastructure that is available today for petroleum and natural gas. So this suggests to us that although there is a significant vision and opportunity for thinking about hydrogen in a low carbon energy system, there are significant barriers as well from an infrastructure standpoint, as well as identifying low carbon hydrogen pathways that are scalable and cost effective. So I'd like to just talk a little bit about some of those pathways of hydrogen production that could be potentially low carbon and also could be scaled to deploy in a future low carbon energy system. So today, as I mentioned, natural gas steam reforming is a dominant technology for hydrogen production. And in the absence of carbon capture, its levelized cost of hydrogen production are roughly around $1 to $2 a kg, depending on the cost of natural gas. This process is associated with CO2 emissions that are roughly 9 kilograms of CO2 per kilogram of hydrogen. One can certainly do carbon capture and integrate it into a natural gas steam reforming process, and this has commercially been demonstrated with two sites operating with significant experience. And the costs again are going to be higher compared to a system that does not have carbon capture, and these costs again vary depending on what you assume about the cost of natural gas as well as the cost of CO2 transportation and storage. In this type of a system, you get typically anywhere between 60 to 90% of CO2 capture, depending on the configuration that's deployed. So as compared to these approaches, there are several other strategies that are being considered with respect to low carbon natural gas based hydrogen production. So one of them, which potentially is a near-term strategy, involves essentially increased use of electricity in the steam reforming process by substitution of natural gas combustion for process heat with electricity use for the reforming process. So a paper a few years ago basically demonstrated this both through modeling and laboratory work to basically show that not only does the system result in a more compact reactor system with better flexibility that can integrate with the electricity grid, but it can also potentially exploit the benefits of emissions reduction that we're seeing in the electric power sector. A little lower technology readiness level option involves thinking about integrating the reforming process with the carbon capture process using a membrane reactor system where electricity and methane are provided as the energy source. This allows us to run the system at a low operating temperature while also potentially producing a pure CO2 product in the process. So this is work from Course Tech that potentially could be an interesting pathway for low carbon hydrogen production. A third approach involves that has gained some interest more recently is based around methane pyrolysis, where you think about high temperature decomposition of methane to produce hydrogen, and instead of producing gaseous carbon in the form of CO2, the process would basically produce solid carbon that could have immense value depending on the state of that carbon in reinforcement applications. So some of these technologies are potentially could be available in the near term, notably the electrically heated steam reforming options, while the other two options of thermoelectrochemical reforming and methane pyrolysis are still relatively early stage technologies. As compared to some of these low carbon natural gas based hydrogen production, there's also growing interest to think about deployment of electrolytic hydrogen production, particularly as we have seen the capital costs of electrolyzers, polymer electrolyte membrane electrolyzers come down over the past few years, and the prospect that we would have increasingly opportunities of relatively low marginal price grid electricity that is also fairly low carbon for many hours of the year. So the chart on the left is just showing you an example of one of the costs, one of the system prices from one of the key PEM electrolyzer manufacturers, where they're sort of anticipating costs today being in the range of $800 to $1,000 a kilowatt of electricity input for multi-megawatt systems, and expecting declines in costs as we are seeing projects announced that are increasingly larger and larger in scale. So the chart on the right here is basically demonstrating the announced projects over the next 4 years for electrolyzer deployment across the world. And there are 2 points to note here. One is that the deployments are growing, but also that the average project size, the largest project sizes are also considerably growing from what they are today, which is in the 1 to 2 megawatts to more in the hundreds of megawatts territory. So these are some interesting developments that has led to a lot of interest in exploring the cost effectiveness of hydrogen in various end use applications. So in the next few slides, I'd like to share with you some of our own modeling work looking into understanding the value proposition of hydrogen use in various sectors. The work I'll be presenting is a combination of work product from a group of researchers at MIDI, as well as collaborations with folks outside MIDI. And I've listed out their names here. So the first study I'll talk about is a topic looking into the use of hydrogen in the industrial sector, and it particularly focuses on evaluating the cost effectiveness of industrial scale hydrogen supply from renewable electrolysis coupled with storage. So this work has recently been published in Cell Reports Physical Science. And the main motivation of this work is trying to sort of understand what are the opportunities for electrolytic hydrogen to be used for industrial scale hydrogen demand. So if you just pull back what is the nature of industrial hydrogen demand, it is primarily focused on steady centralized consumption, which is concentrated at a few locations. So the chart here basically gives you a representation of the various hydrogen production sites in the US. They're typically concentrated at sites where you have a lot of petrochemical activity, and they tend to be large scale facilities that are continuously consuming hydrogen. This industrial scale hydrogen demand has significant potential for growth, as we discussed in the previous slides, owing to opportunities for expanded decarbonization of this sector. So one estimate from the National Renewable Energy Lab as part of their hydrogen at scale analysis puts this number at 5 times the current demand levels. So with this sort of interest in mind, the study wanted to look at basically what is the opportunity for electrolysis to play a role in this new demand that might emerge from the industrial sector. So one option for deploying electrolysis systems is to just connect them with the electric grid and operate these electrolyzers continuously, which would basically maximize the utilization of the asset and therefore drive the entire basically minimize the capital contribution to the overall levelized cost of hydrogen production. And the levelized cost of hydrogen production in that kind of an application would then basically be driven by the cost of electricity. So here is just an example calculation demonstrating what would the levelized cost of hydrogen be at various locations in California, sorted in ascending order of price for different historical electricity price years and 2 different electrolyzer capital costs. So there are a few key takeaways here. So the first takeaway is that if you look at the chart on the left here and the right, there's basically little impact of electrolyzer capex reductions when you're utilizing your electrolyzer, basically throughout the entire year at relatively high utilization of 95% in this case. The second point to note here is that there is going to be large variations in hydrogen production costs depending on depending on the cost of electricity, which historically, at least in the California context, has been tied to the cost of natural gas. More importantly, from an emissions perspective, if you think about the electricity grid today, it is still largely reliant on natural gas. And so this is just showing you an example of the grid emissions intensity in California, which has significantly come down with the adoption of solar in particular. But if you then calculate the resulting emissions associated with hydrogen produced via this pathway, accounting for the energy efficiency associated with the electrolyzer, we would still end up being higher than the emissions intensity associated with natural gas-based steam reforming. So the dotted line here basically is the threshold grid emissions intensity we would need to get to, beyond which grid electrolysis would have lower emissions per ton of hydrogen produced compared to natural gas-based steam reforming. So what we wanted to sort of understand is, if this approach does not lead to emissions reductions in the near term, what are the opportunities for a completely renewables electrolysis system? So we focused on dedicated PV electrolysis systems, and we wanted to look at the integration of the co-location of these assets, PV generation, coupled to an electrolyzer, along with the potential to store electricity either as in the form of using a battery, or to store the product of hydrogen that is produced from the electrolysis process. Since we are looking at an industrial application that requires steady supply of hydrogen, we would like to sort of be able to meet that requirement, and therefore the need for co-located storage becomes important. So our approach here was to think about, rather than looking at average metrics that look at levelized costs, we wanted to understand how do we design a facility like this that accounts for the hourly variability in the resource, as well as the potential CapEx savings that you could have by optimizing the sizing of all of these different equipment. So we basically look at a strategy based on integrated design and operations modeling, where we simulate, we optimize the design and operations of the system subject to hourly production requirements to be within a very narrow band, while maintaining annual production requirements and considering a range of operation constraints related to the various equipment in the system. It's important to note that these types of applications are primarily CapEx driven in terms of their costs, and therefore, sizing of these equipment becomes a critical factor. So we did this analysis for, a range of different locations spanning continental US, looking at, variations in PV resources for a single axis horizontally oriented tracking system. So here I'm presenting to you just some insights that we obtained regarding the optimal design of these systems for a 2030 scenario cost and performance assumptions. And I'll talk a little bit about some of the sensitivities around these choices. But just looking at this particular scenario, we see that the electrolyzer to PV capacity ratio for the optimal system across a range of different locations organized by capacity factor generally tends to be less than 1, which basically suggests that in all of these locations, it is quite optimal to size your electrolyzer to be much less than your peak PV capacity. And this makes sense because basically your peak PV availability is only available for around 100 hours of the year typically. And so in terms of capacity utilization of your electrolyzer, it is cost optimal to size it to be much smaller than your PV system and curtail that excess electricity. Another design criteria is the amount of storage that you need as a function of meeting your continuous hydrogen production requirement for your industrial facility. And so the plot here at the bottom is basically showing you the hydrogen storage requirements as a function of average PV capacity factor. So of course, if you're operating in locations like Seattle, where PV resource is relatively poor, your storage requirements are on the order of 1,000 hours. But if you look at some of the best sites in the country, which are typically locations that have capacity factor in terms of 25% or higher, you're talking about storage requirements under 100 hours. If you look at even within those best sites, there is quite a significant variation between the lowest hydrogen storage requirement at these sites compared to the highest storage requirement at these sites. So this is basically indicating that as we think about design of these systems, it's not sufficient to just treat the variability in PV resource purely in terms of average PV capacity factor, but one really has to look at the temporal variations that exist at each location to understand the needs for storage, but also the sizing of the various systems. So if you look at a little bit further at what is driving the storage requirements for some of these best sites, here I'm showing you basically the hydrogen storage monthly levels for the site with the lowest storage requirement, which is shown in the purple, and the site with the maximum storage requirement, which is shown in the orange here. And as you can see, the bottom chart here is basically showing you the monthly average PV capacity factor at these two sites. So what you see at the site with the largest storage requirements for PV capacity factors greater than 25% is that there is a larger variation between winter and summer capacity factors. And that is one of the reasons that explains the large variation in storage inventory levels and the need for more storage in these types of systems. In contrast, the storage location, the location with the lowest hydrogen storage capacity tends to have relatively flat storage inventory levels and a lower variation between winter capacity factors and summer capacity factors. This location is in West Texas, whereas the location with the maximum PV capacity factor is in is in Southern California, but in the western part of the state. So you get different sort of resource quality in both of these regions that again influences the choice of design of the system that ultimately has an impact on the cost of the system. So if we now actually talk about what the cost of hydrogen production would be from a configuration that involves PV electrolysis coupled with storage, we find what I'm showing you here is a map displaying the spatial distribution and levelized hydrogen cost across the US for this 2030 costs and performance assumptions. And what you see is that they generally tend to track PV resource availability. So you have lower costs in the southern part of the country compared to some of the northwest regions where you see the highest costs. But you also see that some of the best or the lowest cost regions tend to overlap quite well with existing hydrogen production sites, which are marked in the pink here. So these are indicative of potential opportunities for near-term deployment of this type of an approach, whereby you already have an existing hydrogen demand, and this type of a low carbon hydrogen production pathway could be integrated to meet that hydrogen demand. So we'll focus a little bit on some of the sensitivities of hydrogen production costs and the key drivers for these costs at some of these best sites in the next few slides. So if you look at the levelized cost of hydrogen production at the top PV resource sites, we see that typically the cost of PV shown in the blue bar here is the cost that dominates the total levelized hydrogen costs. So once again, this is a result of two factors here. One is that PV is your primary source of electricity input, but also that because of the sizing decisions that you're making, you're oversizing your PV system, and hence your costs are dominated by PV and less dependent on electrolyzer capex and hydrogen storage capex, which are the other major contributors. So locations, again, where you see that PV resource is similar could have vastly different costs owing to the intertemporal nature and PV availability. And you might need more PV capacity in one location to manage that intertemporal variability. So if you then look at sensitivities around electrolyzer capex, which can be quite uncertain given that it's a fairly early stage technology that has limited deployment, what I'm showing you here is the levelized cost at these top 10 sites as a function of the electrolyzer capex. And so what you see is that really with pressure vessel hydrogen storage, which is what we've been focused on, getting to under $2.50 a kg, which would put it in the ballpark of natural gas reforming with carbon capture, really requires significant cost reductions. However, if you do consider the prospect of geological hydrogen storage being available at some of these best sites, which is a practice technology commercially today at a few locations in the US, you could start to see, costs beating the threshold of $2.50 a kg, even at higher electrolyzer capex, which is potentially interesting options for near-term deployment of this technology. So really, our next piece of analysis is going to focus on trying to quantify where the geological hydrogen storage potential is in the US, and then trying to map it out with the availability of renewables, such as the analysis we've done here. So I'm going to take the next few minutes to quickly pivot to another research topic that looks now broadly at the use of hydrogen across multiple sectors. So the previous presentation focused largely on the role of hydrogen for supplying energy for one particular sector, the industrial sector, in a standalone mode. But in many applications, hydrogen use could be distributed in nature and also could be interacting extensively with other infrastructure that's already in the system, notably the electricity system. So these sectoral interactions become important to capture as we start to think about the value proposition that exists for hydrogen across all of these sectors, but also in balancing renewables in the power sector. So some of the questions that these types of integrated sector analysis could answer is identifying least cost infrastructure outcomes that help to decarbonize more than one sector, identifying where natural gas might find the most value as we transition to a low carbon energy system, and also trying to understand some of the interaction effects just within the hydrogen supply chain, both in terms of the choice of production technology and as well as the mode of hydrogen transportation or storage infrastructure that is selected. So the work we did focused initially on a case study where we're trying to sort of understand the interactions primarily between the electricity system and a future hydrogen infrastructure system, where we are focused on sort of two major interaction opportunities with the option of using power for hydrogen production and the potential for using hydrogen to supply dispatchable power to balance renewables in a low carbon system. In this type of a framework, we, for our initial analysis, have parameterized the availability of gas infrastructure and CO2 infrastructure in terms of input cost assumptions for both of these feeds and sinks. And we are primarily looking at hydrogen use in the transportation sector as a starting source of hydrogen demand. So this is a least cost infrastructure framework that we've developed, which is basically a linear programming model at this point that considers supply and demand constraints at an hourly resolution across both these sectors, technology operating constraints, as well as policy constraints regarding emissions reduction. And what we get at the end of this type of a framework are insights regarding optimal investment decisions and their utilizations across the sectors. So we looked at a case study of the US Northeast, where we have sort of estimated hydrogen demand based on 20% fuel cell electric vehicle penetration using historical gasoline consumption data. Within this case study, we consider a range of technologies for power generation as well as hydrogen production. We also consider a range of technologies for hydrogen transportation, either as liquid or gaseous trucks, hydrogen pipelines, and look at its competition with electric transmission as the mode of energy transport. We consider energy storage availability, both in terms of hydro resources in this region, domestically and imported, as well as the option of deploying batteries or pressurized hydrogen storage at various locations. And to account for sort of the hour-to-hour operations of the system, we are modeling the operations of the system over 30 representative weeks of that are selected from historical weather data to sort of represent the variability that one might see over the course of a year. There are a number of different assumptions that go into any type of model like this, and I'll just highlight a couple of them. The electricity load that we're assuming here is for a 2050 scenario based on the NREL electrification future study, and we're considering, as I mentioned earlier, hydrogen demand of approximately 1 million tons per year, which is approximately representative of 20% fuel cell electric vehicle penetration in both light duty and heavy duty applications. So let's look at some of the insights that we gained from this type of an analysis. So what we did was we looked at how the optimal infrastructure choice would evolve as a function of the carbon price on the system that would price the externality of emissions, but also as a function of sensitivity to electrolyzer capital cost assumptions, which is a key uncertainty at this point. So the chart I'm showing you on the top here basically shows you the hydrogen generation capacity as a function of broken down by the various technology types for these two different parameter inputs. So what we see is that at basically no carbon price scenario, the current cost of natural gas makes it basically the dominant source of hydrogen production. And even if we have cost reductions in electrolyzers, there's relatively little penetration of electrolysis in the system. So this is partly driven by the competitiveness of natural gas, but also the fact that the electricity sector does see large adoption of wind and solar in terms of capacity, but there aren't just those many hours of low carbon electricity supply to justify the use of electrolysis for hydrogen production. However, if we introduce a small carbon price of say $50 a ton, then what we see is that the system starts to shift away from traditional natural gas reforming to natural gas reforming with carbon capture for hydrogen production. And if you look at scenarios where you have electrolyzer costs coming down roughly half of what they are today, then you could see a scenario where hydrogen, nearly about 30 to 40% of hydrogen supply could come from electrolysis in this type of a scenario. More importantly, you also see that with a small carbon price, you're significantly increasing the amount of wind and solar penetration across both of these systems. Now, one of the interesting insights that we see from a coupled analysis like this is that we see that CCS or carbon capture shows up much earlier at a much lower carbon price for the hydrogen sector as compared to the electricity sector, where we only see CCS really showing up at a very high carbon price of $1,000 per ton. This is basically due to the synergy that results from having a flexible electricity load in electrolysis-based hydrogen production that can supplement the integration of renewables in the power sector. You see this effect also in the relatively little adoption of battery technology until you get to much higher carbon prices or deeper decarbonization levels. So if you just look at the capacity investment in energy storage, once again, we find that the bulk of energy storage deployments occur in the hydrogen sector, primarily in the form of pressurized hydrogen storage, but also in the form of mobile storage, such as using pressurized gas trucks that provide additional flexibility to the system to balance supply and demand across the region. Here again, the preference to use hydrogen storage as the predominant mode of energy storage in the system is stemming from its lower energy capital cost, and that hydrogen storage proportion continues to increase as we go to lower electrolyzer costs, which is indicative of the fact that the flexibility in electrolyzer operations requires additional hydrogen storage to supplement that, and results in electrolytic hydrogen plus hydrogen storage outperforming the need for CCS-based technologies in the power sector or other types of energy storage in the power sector. So one way to quantify the impacts of sector coupling is to sort of think about look at the difference in the model outcomes from the coupled approach, which is what I've been presenting to you, and compare this against the model outcomes from a decoupled approach, where we basically independently optimize the infrastructure needs for both of these systems without considering these interactions of hydrogen to power or power to hydrogen. So the plot here shows you basically the difference in capacity between the coupled approach and the decoupled approach. The difference in capacity here suggests that a positive value here is indicating more capacity of a particular technology in the coupled approach compared to the decoupled approach. So what we see here is that consistently across the different hydrogen demand scenarios, we see that the coupled approach basically leads to greater integration of renewables in the system, which stems from the fact that the availability of an electrolyzer load that is flexible in nature and can be supplemented with hydrogen storage allows for greater integration of renewables in the power sector. And this increase in renewables comes at the expense of basically reduced requirements for battery storage, but also dispatchable power generation in the form of combined cycles with and without CCS. As we increase the nature of this hydrogen demand, the nature of the coupling between the two sectors increases. And so you see the effect of this coupling showing up at much lower carbon prices as well. You can also sort of think about the impacts of these couplings and coupling between the two sectors in terms of a cost reduction. So if you look at the cost savings resulting from the coupled system optimization compared to the decoupled approach, we see that these cost savings generally tend to rise as we have an increasing carbon price and increasing hydrogen demand, with the maximum savings for the scenarios that we evaluated approaching about 12%. We also see, similar to this, savings on the emissions of the overall system, where essentially having a small hydrogen demand leads to greater emissions reduction in the power sector compared to not having that hydrogen demand because of the flexibility that electrolysis provides to the system in integrating more renewables. Finally, I'd like to talk a little bit about just the insights we have learned regarding the hydrogen infrastructure and its interactions with the choice of hydrogen production modes. So here I'm focusing on two particular scenarios that we have talked about previously. One is a scenario where essentially electrolyzers are very expensive and we don't have a carbon price. So essentially the dominant mode of hydrogen production is natural gas reforming. And then another scenario is where we're looking at electrolysis being the dominant mode of hydrogen supply. And what I'm plotting here is basically the amount of hydrogen transported across the system on an annual basis as a function of these two scenarios, but also looking at the sensitivities to pipeline costs for hydrogen pipeline transportation. So what we see in our base case is that truck-based hydrogen transportation generally tends to dominate, and it's dominated predominantly by liquid trucks. So you see that both in the SMR case, but also in the electrolyzer case. However, as you start decreasing your hydrogen pipeline costs beyond from the baseline level of 100% to about 50%, we start to see pipelines emerging at about 50% of their baseline costs for both of these systems. This suggests that potentially, strategies for retrofitting existing natural gas infrastructure and natural gas pipelines that could sort of meet this cost threshold could be a competitive option for long-term hydrogen transport. Another point to note here is that the mode that involves natural gas reforming tends to involve an infrastructure layout where hydrogen is produced at centralized locations and transported a lot more compared to a mode that primarily relies on electrolysis, where the overall amount of hydrogen transported is smaller than the mode in which you're relying completely on centralized technology. So this kind of suggests to us that the choice of hydrogen infrastructure is also intricately tied to the types of hydrogen production pathways that are selected for meeting these various end use sectors. So this is just a flavor of some of the analysis that we have been doing. I'd like to highlight that this is a framework that can be readily adapted to consider a number of different further questions that are related to the role of hydrogen in a future low carbon energy system. And we'll be tackling these in the coming years, both at MIT and in collaboration with many of you on the call. So some of the opportunities here to think about, both in terms of technology development, relate to trying to use a systems approach such as what I described to you here to understand the competitiveness of emerging technology pathways in production, storage, and transport. Another sort of a compelling research exercise that we would like to sort of undertake is to understand, what are the opportunities for retrofitting gas infrastructure, and at what cost do they actually become competitive with building out new greenfield infrastructure for hydrogen movement. And finally, as we start to think about sector coupling, it's not just about power and transportation, but sort of thinking about the aggregate view of hydrogen that has a key impact on its value proposition. And one of the other aspects regarding hydrogen that is particularly important to consider is the costs associated with last mile distribution. And this framework could be easily adapted to think about the trade-offs between hydrogen infrastructure or electricity infrastructure for last mile distribution of energy for distributed end uses. And finally, as we think about a warming world and a low carbon energy system and trying to plan for infrastructure, while sector coupling does offer some cost savings, one has to be cognizant of the fact that those cost savings come at the expense of increased interdependence across these systems. So one really has to be thinking about not just the cost savings that come from reduced infrastructure layout, but also the resilience and reliability that might be impacted from these increased interdependence. So with that, I just want to summarize some of the key takeaways that I had shared with you today. So we looked at these two particular case studies, one with industrial decarbonization, where we sort of explored the prospect of, renewable electrolytic hydrogen coupled with storage to be able to provide steady supply of hydrogen for industrial sector. And, the key takeaway here is that design matters in terms of how you size these various systems, and is very location dependent. And further, availability of geological hydrogen storage is really a key enabler to getting costs to be competitive in this sector and this particular application. And then on the sector coupling aspect, the main sort of takeaways are that, there is really a role for natural gas primarily in the hydrogen production sector, even under moderate to high CO2 prices, and less so in the power sector. And the flexibility that electrolyzers coupled with hydrogen storage provide drive increased renewables penetration in the power sector and potentially could have an impact on the electrochemical storage needs in the electricity sector. So with that, I'll stop, and I'm happy to answer questions that have probably come up in the chat. So I'll turn it over to you, Rob.
Okay, thanks very much, Derek. My goodness, there's a lot there to take in. And I'm sure there'll be lots of questions. I'm watching the Q&A section, or rather tab, and I'll keep an eye on questions as they come in. But I guess there are a couple of surprises here for me. I mean, you just alluded to one, the viability of natural gas as a hydrogen source, even when you have to implement CCS. A relatively modest premium that looked from your initial numbers that it was maybe in the 50% range, maybe smaller than that in some cases. But I guess that depends on the overlap of production sites and CCS sites and pipelines and local concerns about storage. Is there really a strong overlap between those infrastructures at a large scale that would mean that that's a conclusion that we could draw at very broadly?
So today, I mean, natural gas, natural gas-based reforming is typically, concentrated with petrochemical operations. And if you look at regions like Texas, there are significant sequestration sites, in close proximity of where natural gas reforming occurs, that you could argue that, that is certainly a viable pathway. In the Northeast, potentially, one of the aspects that we didn't look at was to characterize the available CO2 sequestration, right? So I don't really have a definitive answer to say if that could be a showstopper. But in general, if you're the reason you see natural gas reforming with carbon capture being so competitive is that you're seeing even with low cost electrolyzers, there are going to be times of the year when electricity prices are just high enough that it makes the availability of dispatchable hydrogen generation from a source like natural gas reforming that is also low carbon very competitive in the long term.
So we'll be looking forward to your study of geological storage and future work on CCS to help make those economics clear.
Sure.
A couple of other questions as well. One I see here in the list of questions is one that I also had. Trucking liquefied hydrogen around? Seriously? That's our best option? Is that really the case? I mean, I'm surprised.
So when you think about the way hydrogen is moved to support the relatively small refueling station demand that we have that is distributed across the country, liquid trucks are a competitive option based on what we have seen being reported, but also some conversations that we had with some of the hydrogen vendors. So it is largely consistent with what we're seeing in terms of hydrogen infrastructure rollout today. Pipelines really become a competitive option when you have large demand and large supply that allows for sort of efficient utilization of the intensive capital resource. So unfortunately, I think this is the best that we have today. One could also think about, there's obviously issues here regarding congestion on the transportation system that we have not accounted for. And so that's another, important factor. I don't think we want to advocate for liquid trucks as being the solution for large scale consumption across all sectors. But I think as you think about the rollout of the hydrogen economy or hydrogen based end users, trucks offer you sort of that balance of modular investments that can ramp up based on demand increasing down the road.
Yeah. There was a really interesting announcement either at the end of last week or at the beginning of this about NextEra's investment in a 20 megawatt, I believe, electrolyzer in Florida. In other words, they're not storing hydrogen, they're going to produce hydrogen on demand using an electrolyzer and feed it into a gas stream driving gas turbines in their Okeechobee facility to produce electricity. So the water is the storage medium.
Right.
How seriously do you take that as an application, or are they just getting their feet wet with hydrogen and they're going to go elsewhere, do you think?
I mean, so
Yeah.
I mean, I think that, definitely, the opportunity for using hydrogen to balance the variability in renewables is immense. In our analysis, what you found is that that can be as much accomplished by just having a flexible demand source coupled with hydrogen storage, as actually thinking about it from a perspective of providing dispatchable power. So the dispatchable power route, at least in our analysis, we find that it has an efficiency penalty that potentially makes it less competitive than just having a flexible demand source coupled with hydrogen, where that hydrogen could be used for its value, for its value as a chemical or a fuel. So I see sort of potentially two routes in which hydrogen production via electrolysis could support the electricity system in balancing renewables. So it's encouraging to see that electrolyzer deployments are scaling up, and both the strategies that I mentioned rely on electrolyzer deployment. So in some sense, they're agnostic to the choice of pathway that is ultimately the dominant technology. But at least in terms of efficiency, the first approach might have some benefits.
Mm-hmm. You showed a curve early in the going of electrolyzer costs projected over the next several years, not many years, coming down by something like 50%, maybe a little bit more over time. And at the same time, project size increasing. And I just wondered whether the cost reduction you were seeing was really just an outcome of project size increase, or is there they're actually projected to be an intrinsic decrease in cost, electrolytic cost.
So, I mean, my interpretation on this is that it's largely a function of just getting the manufacturing in place to be able to efficiently produce these units at scale. So many of the deployments to date were basically based on hand-built electrolyzer modules. But recently we have seen announcements of, gigawatt level manufacturing facilities from ITM Power and others that are indicating that, really manufacturing here is going to enable some significant cost reduction. So the costs that we have today are not reflecting a cost of a scale technology. And so the scale up benefits are likely to drive these cost reductions in many applications.
I see. There's an interesting question here among the Q&As, basically asking, if you're going to do SMR and produce a lot of CO2 that you then have to sequester, are you potentially using up hydrogen storage sites that's going to end up driving up the cost of hydrogen and reaching some sort of equilibrium that's not nearly as far down the path of hydrogen as you'd like?
So that's a great question. I mean, I think I don't have a well-educated answer at this point regarding the compatibility of hydrogen storage at CO2 sequestration sites. I think there's a lot of work that's been done on mapping out the CO2 storage capacity, both in the US and abroad, less focused on hydrogen storage sites. Hydrogen being a smaller molecule, I would imagine that only a subset of CO2 storage sites are potentially compatible with hydrogen storage. So that's certainly, I think, a very valid question. And thank you for whoever asked that question. It's an area that we should really look into.
Yeah, yeah. And I think potentially that could be part of the future study on geologic potential for hydrogen storage. They're certainly very similar reservoirs.
Yep.
There are questions still coming in. So let's see. I guess one concerns safety. I mean, we all have pictures of Zeppelins exploding in the air in our minds whenever, no matter what, when we hear about hydrogen. Are you concerned that either geological storage or transportation and gas pipelines would lead to safety considerations that could drive up costs?
So, I kind of wear my chemical engineer hat on this and say that, when everything that the chemical industry and the oil and gas industry handles tends to have some sort of safety element to it. And so, as long as these things are done at scale and handled by professionals, I think I don't see many challenges from that standpoint. Certainly, reusing existing infrastructure brings up some more pertinent safety questions regarding, the materials integrity with hydrogen, both within the transportation infrastructure, but also for end use customers with respect to the devices that that hydrogen would be used in. But I think at scale, geological hydrogen storage is practiced, at 5 different locations at thousands of tons of storage capacity today. And, I think when handled by professionals at scale, I don't anticipate that being the bigger challenge. I think definitely there's a perception issue with hydrogen. And so historically, since hydrogen use has been focused on transportation, it has involved convincing the consumer to adopt hydrogen, whereas a lot of the models for hydrogen deployment in the frameworks that we are looking at largely rely on fleets adopting hydrogen where potentially professionals are handling it, and also more centralized end users of hydrogen where the opportunity for mishandling might be lower.
Joe Powell makes an interesting point and then asks a question about geological storage of hydrogen, and noting that I guess, Joe, and correct me if I'm getting it wrong, geological sites, at least he understands them, are limited. And so you'd need extensive pipelines for hydrogen to carry hydrogen to markets from those limited sites, which may be untenable. You have to rebuild a lot of infrastructure or find a way to adapt existing infrastructure for natural gas to hydrogen. So does that push you into a role in which you can really only use hydrogen, generate hydrogen locally, and use local distribution, and for long haul storage or long haul hydrogen, basically pipe around natural gas in the existing pipeline system and convert it locally to hydrogen?
Right. So I think that's a fair point that we have looked at some studies regarding the potential for geological storage in the Northeast and have found little evidence that there may be opportunities for storage here. So I think that is true that geological hydrogen storage sites could limit adoption of large scale hydrogen production. But that said, I think even if you think about distributed electrolysis deployment as a way to produce hydrogen, that still is likely to require upgrading the electricity infrastructure to be able to move the electrons that's needed to be able to supply these large loads. So I think uh, it isn't so much a question of building no transportation infrastructure. It's more a question of building electricity in transportation infrastructure, or more dense energy carriers like hydrogen or ammonia. So I think what we are highlighting here as an area that we want to look into next is I think very pertinent here, which is around identifying what are the technology barriers and costs associated with retrofitting existing infrastructure, because I think that's really our least cost pathway out of this, where if we can find a way to use all the sunk capital, then that will provide us an opportunity to expand the role of hydrogen and decarbonize some of these end uses.
Mm-hmm. It's an interesting question here as well about the possible effect of hydrogen leaks. We're all familiar with the issue of methane leaks from gas pipelines and gas facilities. Methane is a potent global greenhouse gas. Hydrogen isn't one, but what if you had massive or chronic hydrogen leaks? Have you learned anything about the potential impact?
So I've not, to be honest, I've not given that much thought, because I think that's not how the industry operates, at least today, in the scale in which it operates. We do have some limited pipeline infrastructure, and hydrogen leaks are not what dominates their operational integrity. So I think this boils down to the question of thinking about materials integrity of hydrogen with respect to existing infrastructure. When you're building new infrastructure, you will obviously select the right materials to be able to deploy that. But I think that question of leaks is certainly something that has to be factored in as you think about codes and standards for hydrogen deployment. And so there are significant additional, I believe, safety standards that go into thinking about hydrogen deployment that accounts for the population density of a particular area in case a pipeline leaks and so on and so forth. So there are mechanisms in place. I'm not the expert on this, but I'm happy to have a follow-up conversation on that and learn about it a little bit more from whoever is asking that question.
I think it's a great question. I mean, these questions were not asked when HCFCs and HFCs were introduced, and it was only later discovered that they were having a terrible effect on the ozone layer and other things. And you could imagine hydrogen mutating in the presence of light and other chemicals in the atmosphere. It would be an interesting thing to follow up on. Thank you for that. Thank you for that question. We're getting close to the end of the hour, and I'm just going to scan here to see if there are any further questions that have come in that we haven't more or less addressed. It's one thought that I had, and there is a question relating to this in a sense, is that in your study of PV and hydrogen, you come away from that with the idea that poor Seattle isn't going to see a lot of hydrogen. But of course, that's possibly not true if they're able to build a lot of wind, for example, or procure a lot of wind locally. Can you say anything more about that and the ability of especially northern states like Washington to be able to use hydrogen for electricity storage on the grid, where they're going to need it more than anybody?
Right. So I think there are 2 points there. So one is, many of these northern regions are actually have access to hydro resources, significant hydro resources. So they are in effect a comparative option for hydrogen production. So if you see Air Liquide, I believe, is deploying like a 20 megawatt electrolyzer to supply hydrogen to the Boston market, and they're doing this in Quebec using hydro resources there. So that's one point to think about. Wind resources, both offshore and onshore, are certainly a competitive option. In our initial analysis, we didn't go after wind primarily because of its relatively lower aerial energy density, but certainly if it's offshore, that becomes less of an issue, and you could explore the same analysis that we did and look at the competitiveness of wind. And in some locations, it might be more competitive than PV for sure.
I see. One final question relating to again, the reuse of infrastructure, and this time maritime infrastructure. If trucks are a great idea for moving hydrogen around in the near term, how compatible is LNG technology, or how close is LNG technology and LNG shipping to what would be required for hydrogen to make LNG pathways a viable way of moving hydrogen around the world? Or is that a stupid question because we have an opportunity here to produce hydrogen locally, either from electrolysis or from methane reforming?
I mean, I think moving hydrogen via ships is I think a very important consideration, particularly if you look at densely populated regions of the world where the land and the renewables resource may not be justifiably large enough to be able to exploit for hydrogen production. And so you have heard of proposals where a region like Chile, which has a lot of very good renewables resource, could be looking at exporting hydrogen to Southeast Asia and other markets there. So I think that's certainly a very competitive option. Whether you can retrofit LNG ships, I think is more a question of hydrogen and LNG operate at different boiling points. There are different materials integrity issues with the enclosures that you need to manage. Hydrogen has a much lower energy density than LNG, and so there's greater payload that you'll have to carry effectively in these systems. So it may not be a like-for-like swap, but I think there are hydrogen ships being envisioned for short-distance transport. So I think that's a very plausible pathway. And I would also make a point here about it's not just hydrogen; it could be hydrogen-derived carriers. So ammonia could be a very compelling opportunity for long-distance shipping that can get to the energy density levels of LNG.
Great. Well, I'm afraid we've come to the top of the hour. You've told us a lot of answers based on your modeling work and initial analysis. Obviously, there are a lot more questions
Of
that
course.
need to be answered, and it'll be exciting to continue to follow your work and the work of others going on in the LCECs over the next several years. So I'd like to thank everyone for your very interesting questions and for participating this morning, and also, again, thank you, Derek, for joining us.
Thank you.
These slides will be available online, and questions that we haven't gotten to online, we'll do our best to answer. So look out for those. If you'd like to email questions, please do feel free to email them to us, either Derek directly or Renan Miller, who is the Executive Director of the centers. Thank you all again very much.